Okay, let's start a new chapter on taking a bit more depth in enthalpy and discussing something called Hess's law. So our inquiry question is, how much energy does it take to break bonds, and how much energy is released when bonds are formed? So here we're treating chemical reactions as bonds breaking and bonds forming, and looking at the energy that it takes to do both. So putting energy into break bonds, if you break something, you're putting energy into it. And when we form chemical bonds, when atoms attract to each other, they release energy. Okay, so here, syllabus point. Explain the enthalpy changes in a reaction in terms of breaking and reforming bonds, and relate this to the law of conservation of energy. Okay, so chemical reactions involve breaking bonds of the reactants and making new bonds in the products. As I was just saying, we need to put energy in to break bonds, and I like to think of it as this model, and I'm using the diagrams on the right here now, where you've got a bond represented by a spring. Okay, to pull them apart, you've got to put energy in to stretch the spring away and then break it. Okay, and then when you put them back together, they're attracted to each other, the different atoms, and they come in nice and close, and they sit close, and they release energy in that. That's the opposite energy of breaking those bonds. Okay, so here in my diagram, we've got some molecules. We've got one of the red molecules and two of the white molecules, and we're putting energy in this step, in the second step here. We're putting energy in to break these bonds, to stretch these bonds away. So we're putting energy in to separate them. So in the third one here, we've got completely separated atoms. Okay? And in the fourth one in my sequence here, we're forming new molecules, so we're releasing some energy. So as these atoms are attracting each other in 3, they release energy and they form new bonds, and we get finally new molecules. I'm guessing I've modeled it on water, haven't I? Look at those Mickey Mouse ears. So I'm starting with one O2 and two H2s up the top, and I'm breaking those bonds, and I'm forming 2 molecules of water down in 5 in there. So that's a good model to think about how we're going to approach this whole chapter. Okay, let's focus a bit more on attraction here. Okay, so we know that atoms are attracted to each other. Okay, positives and negatives. The positive of the nucleus will attract the negatives of the other atom, the electrons of the other atom, and they'll attract each other. Okay, and so what we've got here is a diagram of energy on the left-hand side, what we've been dealing with a lot in our diagrams lately. But on this x-axis here, this r is the radius between 2 atoms. Okay, and so out here, the radius between 2 atoms is very large, to infinite. Okay, and as you're getting closer this way, as you're reducing the radius and you're bringing these 2 atoms closer, there's an attractive force between them, and that's electrostatics. Positive is attracting negative. So the positive in the nucleus is attracting the negatives around the outside of the other one, and vice versa. So we get this attractive force, and as they move in closer together, there's energy released. Okay, so if you move them this close together, you lose this amount of energy. Okay, whatever that is on our scale here. And you bring them closer, and you lose even more energy, and more and more and more and more, until they reach this state where they've lost the most energy. Okay, and this is the most stable state, because on the other side, as you move them closer and closer together, you're not losing much energy anymore. In fact, you reach a point where you've got to put energy in to push them together. Okay, here they're getting too close, so the light charges are too close together, and they're repelling each other. The repulsion of light charges is overcoming the attraction of opposite charges. Okay, so it's a bit of a balancing act, and atoms form bonds because they want to reach this sweet spot in between, the balance between the attractive forces and the repulsive forces, and it's this sweet spot here. So for this atom, I forget what it is here, but when they're infinitely far away compared to when they form the bond, it's 436, negative 404, I can't talk, negative 436 kilojoules per mole. Or when you make this bond between them, you get 436 kilojoules per mole. Okay? So if they're going closer together, yeah, that energy lessens until it becomes positive, and you've got to like push them together, put energy into the system to get them to come closer. But this is why they form bonds. It's that nice sweet spot in this energy well, we sometimes call this. Energy well. It sits at the bottom of the energy well. Okay, so let's apply this to what we're talking about in that other slide, hydrogen and oxygen reacting with water. So here we start with H2 and O2, and we're going to break their bonds. Let me just write down here, 2H2. Oh, help if I could write 2 and not H. 2H2 and an O2. There's our reactants. I'll put a plus in the middle. We're going to break their bonds, and we have to put energy in to break bonds. So we're moving up there. And so here, instead of 2H2 and O2, we've got 2O and 4H. Okay, we've broken all the bonds. They're just individual atoms. Okay, and the next stage is we're going to make bonds. Making bonds releases energy, so we're going negative on our energy scale. And in this case, we're going negative even more to where we started, because we can look at the enthalpy of the reaction, but we'll get there soon. And we're forming 2H2O, okay? So we had two O's. I was going to write 2O2 there. We've got two O's up here and four H's, and we started as two H2s and an O2, okay? So we've gone up, we had to put energy in to pull them apart, and then we've got energy released down to water. Oh, look, I've written it here, okay? And so this difference between where we started and where we're ending on our reaction scale here, sometimes RxN is short for reaction, our difference is our enthalpy of our reaction over here. And in this case, delta H is negative in this case, okay? But we can have some where they end up here where it ends up being positive. But for this reaction here of hydrogen and oxygen forming water, enthalpy is negative, okay? So the enthalpy is, as I've written down the bottom here, the energy required to break bonds plus the energy released when new bonds are formed, okay? I know it's got a positive in there, but you have to remember that this is a positive and this is a negative, okay? So just adding the two energies together, once you've got the right sign, will give you the enthalpy, okay? Here, the negative is much greater than the positive, so we get a negative enthalpy. Oh, that's exactly what I've just talked about in this slide here. Okay, oh look, I've given a different example here, one that's endothermic, okay? I've got nitrogen gas and oxygen gas going to two nitrogen monoxides, okay? So here we're starting off, here's our reactants, N2 and O2, okay? We're putting some energy in to break bonds, and so we got two hydrogen atoms and two oxygen atoms, and then we're releasing energy in making these bonds into 2NO. And we've got our enthalpy as the difference between where it began and where it started off. And in this case, for this reaction, it's positive, okay? So our energy that we put in to break bonds, our positive there going up our scale, is much bigger than our negative coming back down. So our enthalpy is positive. Okay. That's just what I said there. Okay. Let's relate this energy differences to chemical stability and reactivity, because it all joins up and it's all a measure of the same thing, okay? So the stability of a molecule is a measure of how difficult it is to decompose or break it up into separate bits, okay? must happen by heat or electrolysis in the absence of air. Otherwise, okay, if you try to break something down in air, sometimes it can just not break down but turn into a combustion reaction once you put energy in, okay? So the arrangement of atoms with the lowest energy is therefore the most stable, okay? The arrangement with the highest energy is the least stable. So from our earlier example here with water, you can, with hydrogen and oxygen transforming to water, you can see that water was a lower energy than the hydrogen and oxygen separated. So out of those two options, water is the more stable. It's also the more unreactive, okay? The more stable it is, the more unreactive. It's also the more energy in the bonds too. Okay, so hydrogen and oxygen gas separated is a higher energy, so they're less stable and more reactive in comparison to water, okay? The most reactive here, and it should come as no surprise, is way up here, where we've got completely separated atoms, okay? A lot of energy's gone into completely separating them, so they're the most unstable and the most reactive. Okay, so out in the real world here, where we've got a lot of atoms very close to each other, ready to react, these are very uncommon, okay? Individual atoms happen very, very rarely, and when they do happen, they're so reactive that they'll react away in the matter of pico or femtoseconds. They don't last very long because they're very reactive, okay? Okay, I think all I've done here is kept the same wording, but I've just picked up the nitrogen and oxygen example here. And so here, nitrogen and oxygen separated are lower energy than the nitrogen monoxide. So they're much less reactive. Okay, so they're more stable, nitrogen and oxygen separated. Nitrogen monoxide is more reactive and less stable. And again, the separated atoms are the least reactive. Are the least stable and the most reactive. Okay, higher up in energy, more reactive, less stable. What have I done here? I've just got the same thing, haven't I? Anyway, let's skip on to here. What have I done here? That's just the same slide as earlier. Alright, let's move on to Hess's law here, okay? Let's apply this. So, or maybe I should do another video. I'll do another video.